So this talk is work is with Daniel Genkin, me here, Patani, and Eran Tromer, and it's about what solves a problem that I'm sure you've all encountered, which is when you're talking to a colleague or a friend or whoever over a voice over IP, sometimes they would appear as if they're not even paying attention to the really interesting things you're saying, and you wonder what's happening on the other end of the call. Are they actually, listening to you doing science, or just scrolling through their feed or whatever? And so in this situation, you're already getting an audio feed from their environment, right, playing on your speakers or headphones. But you can't really tell what's on their screen, and this is what you're interested in. So, but the audio that you're getting is coming from a microphone that's pretty close to their screen, typically. And so can you use that? Well, it turns out that when screens render visual content, they emit noise. And this noise is pretty subtle. Usually we don't mind it. But what if this noise does have some correspondence with the content that's being displayed on your screen? So if that's true, that would cause more problems than for bored colleagues, because people do a lot of things with their screens, a lot of private things. For example, they surf the web and they input credit card numbers, they nurture weird obsessions that they don't want other people to know about. And all the while, it's common to have microphones being placed next to screens. And it's even common to have them recording. If you're interacting with the Google Home or an Alexa device, then it's recording. And if you're video chatting, or if just the third-party app on your phone decided to and has permission to. So audio is, in a sense, it's very available. And it's, in some sense, it's more strongly, more highly available than the electromagnetic leakage that we've seen, the famous Van Eck leakage. That's also a visual content. So to find out if we do have this leakage of visual content onto audio signals, we drew a zebra on the display, and the zebra is just a series of black and white stripes. And we recorded the zebra, and we saw and we visualized the signal using a spectrogram, which shows the frequencies through time, the frequencies in the signal. And in this spectrogram, there is a predominant frequency component at 4 kilohertz. Now, where is this 4 kilohertz coming from? It could be coming from the fact that the screen is rendering content in this raster pattern, and it refreshes 60 times a second. And since it has 66 stripes coincidentally on this screen, then the math shows that it will render 4K stripes at regular intervals every second. So this 4K and this 4K could be related. We're not sure, but to find out for sure, we're going to change the stripe width of the zebra. And every time we change the stripe width, we see that on the visualized audio signal in the spectrogram, the frequency of rendering stripes appears. So this is kind of a smoking barrel for a leak. We know that there is definitely a visual to audio leak here. And so we tested it with a bunch of screens, and they all presented the same leak. This is just a few examples on how it looks like with different screens, but we tested it with a lot of screens, like over, 2 dozen at least, and more. And we tried to figure out where this is coming from, and we localized the leak to the screen's power supply. And we can conjecture that it stems from different power draw of different values when you render different intensity pixels. And we've seen a similar thing before with in our own lab with Genkin et al.'s 2014 acoustic cryptanalysis, but that was for computation, not for visual content. Now, so far, the spectrograms I showed were for lab conditions. But in our attack scenario that I discussed with a bored colleague, we had plausibly a webcam microphone or any commodity microphone that the person is using to video chat with. And the audio was being lossily compressed and transmitted over to you over the internet. And so the question is, does the leakage persist over these conditions? So we did the zebra test, the exact same test, but over a Hangouts connection. And we saw that we can still see the frequency of the zebra in the spectrogram that we visualize. And we could even see it when we placed a Google Home or an Alexa device next to a screen, presented a bunch of alternating frequency zebras, and interacted with the smart speaker. The smart speaker sent our recordings to the cloud. We downloaded them, and we could see the zebras that were being displayed on the screen while we were interacting with Alexa close to it. So it even persists in these conditions. Recording the leakage and observing the leakage with a smartphone was easier. And we could also, you can even do it at a distance of up to 10 meters and still, with this fancy parabolic mic, and still see the zebra frequency in the spectrogram. So what can an attacker do with it? Because an attacker is not interested in zebras. They are interested in maybe extracting the websites that the victim is visiting, maybe snoop on the victim's on-screen keyboard, and maybe even extract text. And we're going to do all these things. And the way we're going to do all these things is, first I'm going to explain how we denoise the signal, and then I'm going to go over the attacks one by one, and they all rely heavily on machine learning. So denoising starts with the observation that there is a signal that corresponds very highly to pixel line intensities or brightness. That is, in many screens that we tested, we saw the signal modulated on top of a carrier signal. In this case, a 32 kilohertz carrier signal. Now, when the modulated signal is easier to extract in a clean way, so we demodulate the signal and use that. Another observation is that we have a lot of redundancy in this leakage because the screen refreshes 60 times a second. So a natural approach would be to chop the signal into 60 chops per second and average the chops, and we're supposed to get a much higher SNR signal from that because the noise is expected to eliminate and the signal will persist. But this has some challenges. We have some unknown measure of drift that changes with time, and so we can't exactly know where to chop. We have some jitter and anomalous sized chunks that completely impede uneven attempts of synchronization. So, and if we chop at the wrong places, we might end up eliminating the signal rather than the noise. So we have an approach to solving that. I'm not going to get into all the details, but we do extract very clean signals, and we do have a very accurate way of chopping the signal and averaging it. Okay, now I'm going to start talking about the attacks themselves. So the first one will be website distinguishing. And website distinguishing starts with the attacker displaying a bunch of websites on a screen, on a training screen, and he records the traces of the screens while the websites are being displayed, and he attaches the identity of the website that was displayed on the screen to every trace of the screen, and he uses these traces to train a neural network that this is what it's expressly trained for, to take a trace from the victim screen and tell what website the victim was on. And we are using convolutional neural networks. Those are pretty effective with time series data, which is what we have. And we see that this is no exception. We could distinguish what website the victim is visiting with pretty high probabilities. And in these first three rows in the table, we see the results for distinguishing between about 100 websites. We even did it with a smartphone, and we did it at a distance. And the last row shows that the results for doing it, for distinguishing between 10 different websites and the activity of the video chat window. And this is done over the video chat, so with the recordings taken at the other end of the call, like in our original attack model. Okay, so now I'm going to talk about the on-screen snooping attack. So this is how a typical on-screen keyboard looks like. The on-screen keyboards are naturally considered safe against acoustic emanations from keyboard attacks because they don't have the same acoustic emanations that mechanical keyboards do. And they are sometimes even required, for example, by some online banking websites require that you input your password using an on-screen keyboard. And so they seem like an interesting target to attack. Now, these on-screen keyboards, they typically have this property that when you press a key on the keyboard or even when you hover above it, there is a visual footprint to that because the user wants indication of what key is pressing. And so we can apply a very similar attack to the website distinguishing one, except we're going to distinguish individual keys. And this works surprisingly well. So for a horizontally laid keyboard, we could figure out the right key in 40% of the time and 70% of the top 3 guessed keys. And for a portrait layout keyboard, we got very high accuracy that practically enables us to extract whole words. Now, extracting whole words is more complicated because there are some misclassifications, and also because there is some ambiguity with clicking the same key twice. That doesn't have a distinct visual footprint. But we have this procedure that narrows down the word that was being typed to a short list of about 10 words, and the correct word appears in this short list a very high percentage of the time. Here we got comparable results attacking with the smartphone and attacking with our high-end equipment. Sorry. Okay, now I'm going to talk about the text extraction attack. So text extraction, we can't directly apply a classifier because we don't exactly know what the classifier will output. It's an open world problem, so we need a generator. We need something more sophisticated. But what we did was we assumed that every character in the text is in a specific location, and we trained a separate classifier for each location that required us to chop the signal up to contain just a portion of the signal for the classifier training. And we applied error correction using the fact that the victim is not typing gibberish, it's typing English, and specifically words. And so our per-character accuracies gets pretty high, and in over half of the cases, we could extract the exact word, and this is the exact word out of thousands or tens of thousands of possibilities. So again, an open world. There are some limitations to this attack. We used a large monospaced font and a known layout, but still it extracts pretty fine-grained information, and that's nice. The last thing I want to talk about pretty briefly is the fact that the attacker plausibly doesn't have access to the physical access to the victim screen. So this is a problem in many side channel attacks. So can the attacker train on their own screen at their leisure and then attack the victim screen at attack time? And for this, we have to train and test on different screens. Now, is this possible? Well, maybe, because at least for screens of the same model, the correspondence of the signal, of the audio signal with the screen content seems very similar. And this is even true when we attack with a different, or when we record with a different setup. The correspondence is similar, except, well, if we record at the distance, the signal will be lower, as in this graph. But there is some degree of overfitting for our convolutional neural networks to a specific screen, because screens do have screen-specific traits in their audio signals. So to eliminate this overfitting, what we did was we evaluated the methodology of just training with more screens. And we did a pretty extensive evaluation here, recorded with 10 screens, and took a bunch of informative subsets of them. And we found that the trend is that when you train with more screens, it does eliminate the overfitting. And if you train with a lot of screens, you might get accuracy that's comparable to training and testing on the same screen. This has been our talk. Just to conclude, microphones are everywhere. Audio is very available, and it might convey on-screen content. And so the 1,000 words in our paper are worth the picture on the screen, and that's it.
Thank you. So we have time for questions. I guess the obvious question is to ask what your co-authors were doing during meetings.
Well, I'm so interesting that they were definitely listening to me.
Very good, very good. Okay, yeah, I guess. I think they got you first.
Thanks. Hey, Ben Ransford, that was really cool. Do you think you'd ever be able to reconstruct a screen image?
Well, our results are currently that you can extract text is the most fine-grained thing we can do. We could do. It's a topic for future work.
Luc Desetaus from Samsung Research America. This might be in the paper already. I haven't had a chance to look at the whole thing, but do you have any insight into, as screen technology develops, in the trends that it seems to be going, larger screens, larger resolutions, thinner displays, do you think they'll become more susceptible to this attack or less susceptible?
That's a good question. So all I can say is we tested, the screens we tested were both old and very new. So we tested screens from 2013 and screens from 2017, and we did not notice any deterioration in the signal. What we saw was that they leak in the same way, in the sense that we could see zebras in the audio signal. So that's what I can offer.
Hi, I'm Armin from Avast. Is there a benefit of using multiple microphones on the same screen?
We did not try. Why would you use multiple microphones?
So you get, maybe you can reduce the noise in some traces? I don't know, that's the question.
I'm not sure. I'm not sure. There are specific locations on the screen that leak, where the signal is stronger. But I don't think the signal is different from different locations on the screen. So I'm not sure recording with two microphones would, yeah.
Thanks.
Come back to you.
Hi, this is Synesthesia from UC Irvine. Great talk. I had a question. Do you have any countermeasures for this attack? Do you have anything in your mind?
Since like it affects so many screens that are already there, and it's a physical trait of the screen, you would have to change to modify the way that you build screens, and you would have to add either shielding or more noise to eliminate the signal, and so yeah, those would be the types of mitigations, and we currently don't see screen manufacturers rushing to adopt these mitigations.
One general idea we have similar works. It's on a different machine, but we try to update the software. So when you are consuming power, it is just something that's always the same, and you don't see the noise on the system.
Right. So here you would have to. There are defenses against Van Eyck leakage that change the font a little bit, so that it's I guess at least at the level of a screen line, of a pixel line, it remains consistent. You could do that with software, yeah. With sensitive software, you could do that. Yeah, we have more details about that in the paper.
Thank you.
Sure.
Okay, one more quick question.
Hi, this is Gong Jiajun from HKUST. So when you do the website fingerprinting, I just wonder, how do you collect the data? How do you train? You train on the same data and test on the same web pages? And does the loading time of a web page affect your accuracy?
We waited until I'm not exactly sure, but I think we waited until the page got loaded using the Selenium API for that. But we also waited a few seconds after so that the page was loaded. And we didn't scroll through the page, but there were a lot of websites with dynamic content, and just that's because we took the 100 most popular websites. And yes, for the first question, the training and test sets of websites were the same. Does that answer?
Yes, but the victim could visit any other web pages in reality. And also, I think, how do you know the loading time of a web page? How do you know the end and the start of the web page load?
So that's true. For an acoustic adversary that can listen to what the victim is doing, they might be able to tell, according to clicks, when they're loading a web page and when it's done, plausibly. And definitely there are other websites. So the top 100 websites is not enough, but it's a lot. And it shows how, that very powerful distinguishing capability. The adversary that tries to tell whether or not you're doing one activity or a bunch of other activities is a more plausible adversary. Yeah.
Rest offline, and let's thank the speaker again.